In the 1940s, during World War II, the British scientist, engineer, and inventor Burns Wallace, in an article titled Spherical Bomb Surface Torpedo, described a theoretical concept, a widely used and innovative attack method in which a bomb would be dropped and would bounce several times over the water before hitting its target. Afterwards, the bomb would sink and explode underwater, hitting and destroying the foundations of the target. The bomb needed to bounce over the water to avoid the deadly anti-submarine and anti-torpedo nets, which were one of the main and most effective defensive measures against possible attacks used during the World War II. And in a short time, with the contribution of other scientists, Wallace's idea was brought to life. And these types of bombs became known as bouncing bombs, which would make Wallace very famous shortly afterward. These bombs were intended to destroy valuable and important targets considered unreachable by conventional attack methods. Among these targets were warships and, especially valuable, the German hydroelectric dams. Wallace's heavy bouncing bombs, weighing just over 4 tons, were dropped from airplanes, and during their descent, reached speeds of about 400 km/h, while spinning backwards at around 500 revolutions per minute. A key feature that improved the bomb's accuracy was the height it could be dropped from, and its ability to bounce multiple times over water. These bounces over the water were previously calculated so that when the bomb stopped bouncing, it would be just a few meters away from its target, which was usually hydroelectric dams. Next, the bomb would sink, and as it sank, a pre-programmed hydrostatic fuse was responsible for determining the exact depth for detonation. And when that depth was reached, the bomb's heavy 3-ton explosive charge was detonated, generating powerful underwater shock waves that caused massive and severe damage, almost always resulting in the dam breaking.
Take a good look. The height looks good, Arna. You have to put the pressure on the green one.
It's at 60 meters now. Make it work. Bomb away. Impact, Arnie, it was perfect!
But Wallace's bouncing bombs were just a small sample of something much bigger that was yet to come. In a 1941 article titled A Note on a Method of Attacking the Axis Power, Wallace described an attack method in which a large and heavy bomb would explode deep underground near its target. This explosion would send powerful shock waves through the ground against its target's foundations, completely destroying it. Shock waves travel more effectively through the ground than through air, and thus the 5.4-ton Tallboy project began, which would later be replaced by a larger version, the Grand Slam, weighing 10 tons, the largest bomb used during the World War II. These bombs were known as seismic bombs because they buried themselves deep into the ground before detonating their large and heavy explosive charges, damaging houses, bridges, buildings, viaducts, and everything within a close radius of the explosion. In March 1945, 2 Grand Slam bombs pierced through 4.5 meters of reinforced concrete roof belonging to a German submarine shipyard, completely destroying its interior. At the same time, another Grand Slam pierced almost 2 meters of reinforced concrete roof in another part of the shipyard, causing a partial collapse of the roof. On March 21, 1945, during the attack, the Arsberg Viaduct took a direct hit from a Tallboy right in the center, which led to the complete collapse of the entire central part of the viaduct, with the ends of the viaduct being torn from their support pillars, resulting in the collapse shortly after of all the pillars to the east of the viaduct. And on June 8 and 9, 1944, the roof of the Salmore Tunnel took a direct hit from a Tallboy, which went through 18 meters of walls and exploded inside the tunnel, leaving behind a hole about 30 to 35 meters in diameter, thus demonstrating the incredible penetrating power of the bomb. The Tallboy and the Grand Slam were dropped from planes at altitudes of about 13,000 feet, or about 4,000 meters, and during the fall, they spun at extremely high speeds. This spin was caused by the angle of the fins on the tail of the bomb, making the bomb take advantage of the gyroscopic effect, which stabilized the bomb, increased its accuracy, and made it easier for it to penetrate the ground. A few moments before impact, the tail of the bomb was ejected and a rocket engine powered by petrol was activated, increasing the bomb's speed to over Mach 1.3, about 1,600 kilometers per hour, which caused tremendous impact. This allowed the bomb to easily pierce reinforced concrete walls over 6 meters thick or penetrate 40 meters into the ground, so the bomb could go deep into the soil or into reinforced concrete fortifications several meters thick, often lined with a thin layer of specially treated steel, without the bomb disintegrating. To avoid disintegrating right at the beginning, the casing of the Tallboy and the Grand Slam needed to be extremely strong and resistant. For this, the casings were made from a single piece of high-strength steel, which provided incredible resistance and allowed the bomb to survive major impacts before exploding. In general, the Tallboy and the Grand Slam were seismic-type bombs, with 854 Tallboys and 99 Grand Slams built, of which only 42 were used. The Tallboy measured 6.4 meters and had a diameter of about 1 meter, while the Grand Slam measured just over 8 meters and had a diameter of 1.17 meters. With both bombs making use of a powerful explosive called Torpex, which is composed of 42% RDX, 40% TNT, and 18% aluminum powder. In the 21st century, this type of bomb became known as a bunker buster, used to destroy deep underground military fortifications. And they are technologically much more advanced than the seismic bombs of the past. That's because nowadays, besides penetrating the ground or several thick layers of reinforced concrete walls, they are also capable of penetrating mountains and breaking through thick cast steel doors. And they can even count the number of floors the bomb has passed through, allowing it to explode only on a specific pre-programmed floor. To achieve this, microphones are used to listen and microcontrollers work together to count the floors as the bomb passes through them. Currently, the American GBU bomb family is the most widely used in real war scenarios, especially in Iraq. The latest versions of the GBUs, such as the GBU-28, use Eagle steel, an extremely strong, high-performance, and low-cost steel capable of withstanding major impacts. In a demonstration test in Nevada, in the United States, a GBU-28 penetrated 6.7 meters of reinforced concrete ceiling, which belonged to a decommissioned missile facility. And even worse, after penetrating the ceiling, the bomb still had enough kinetic energy to continue traveling further into the facility. Therefore, the GBU-28 is capable of penetrating just over 6 meters in reinforced concrete structures or 30 meters in soil, making it one of the current bombs with the greatest penetration power against reinforced structures. That was until around 2013, when Boeing presented the results of its joint work with the Research Laboratory of the United States Air Force, which resulted in what became known as the Massive Ordnance Penetrator, or simply MOP, a 14-ton bomb capable of piercing mountains and penetrating up to 61 meters into reinforced concrete structures. In fact, the development of this bomb was so complex that the project was abandoned early on due to engineering problems and lack of funding. But the project was reactivated in 2007 because of Iran's continued advances in uranium enrichment for the creation of atomic bombs in heavily reinforced underground facilities. In general, the operation of a bunker booster is based on a balanced, delicate, and complex dance of various physical factors that designers have to take into account during the bomb's design. Among them are the type and density of the material the bomb is made of, the altitude at which the bomb will be dropped, air resistance, the weight of the bomb's terminal velocity, the angle at which the bomb will penetrate the structure, the force of gravity, among several other aspects. So to make a bomb capable of penetrating even deeper, designers have 3 options. They can make a heavier bomb. The greater weight will give it more kinetic energy, that is, higher speed at the moment it hits the target. They can make the bomb smaller in diameter. The smaller cross-sectional area will mean that when penetrating, the bomb will have to push aside a smaller amount of material, whether it's concrete or earth, meaning the bomb will need much less speed at the moment of impact to penetrate to the same depth. The GBU bomb family follows this principle. And finally, they can make the bomb much faster to increase its kinetic energy. And for that, they need to install some kind of rocket motor on the tail of the bomb, which will be activated a few moments before impact, thus increasing the speed and the force of the impact. However, it makes the bomb's design more complex.